Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. Happy to try and answer questions. And I see that there are quite a few that have come in to our form or are saved up from previous weeks. Let me see what I can see here. Okay, there's one from Parmenides asking, what is quantum chemistry good for? Anything interesting? All right, let's talk about chemistry. I've been trying to learn about chemistry recently. When I was a kid, I was really interested in physics. I knew quite a lot about physics. I really didn't care about chemistry because I thought it was all about taking different white powders and pouring them into liquids and seeing what happened, and nothing interesting ever happened. The most interesting thing that ever happened, I think one chemistry experiment I was doing was I just mixed a bunch of random things together in a plastic container. And one of those things was carbon tetrachloride, I think, which dissolves plastic. And so that was exciting. That was about the most exciting thing that ever happened. And I couldn't really see why one would care about chemistry. Okay, I've changed my mind 50 years later or whatever. And chemistry is really very interesting because it's very sort of precise and formal in a way. You've got molecules and they have a certain structure and they kind of interact with each other in ways that are very much like the ways that we might write down sort of equation-like things and they come out with very precise results. So let's talk a little bit about chemistry and what's involved in chemistry, and then we'll talk about quantum chemistry and so on. So in sort of a typical case, first question is you've got a molecule and it has a bunch of atoms, and the atoms are connected together by, and usually characterize the connection by bonds. You've got, let's say, I don't know, we've got water, H2O. That's an O for oxygen and H2, two hydrogens. And so somehow those atoms stick together in a certain way. A typical atom, well, has a nucleus, which has a bunch of protons and neutrons. In the case of hydrogen, in the simplest case, there's just one proton as the nucleus. In the case of oxygen, it's, let's see, I think it's 8 protons, 8 neutrons. Is that right? Oxygen 16, I think that's right. But that's what its nucleus is. And then it has usually it has the same number of let's count it out: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. Yes, it is 8. It's the 8th element, which means it has 8 protons, and in its kind of most ordinary state, it has 8 electrons as well. So you've got this oxygen atom, you've got 2 hydrogen atoms, and how do they get stuck together? They get stuck together by a fairly complicated process that involves kind of the exchange of electrons between the hydrogens and the oxygen, so-called covalent bonding. And the way the periodic table works, the table of elements, it kind of gives you an indication of how many how many electrons are available for exchange by different elements, and that's determined by the column of the periodic table that things are on. So oxygen has some two such sort of available electrons, and that's what it sort of exchanges with the hydrogens, each of which has one such exchangeable electron. That's a very approximate way of describing it, and the sort of the true story of that in the level of sort of official physics is really quite complicated. And the picture that one usually has of it in sort of elementary chemistry is something which is probably a decent approximation, but one has to understand it's an approximation. So in reality, there is a whole elaborate calculation of what the probability to find an oxygen atom in this position and hydrogen atoms in this position and so on. But when you kind of think about it in terms of elementary chemistry, you say there's an oxygen here, and you can even make it with balls and sticks, and there are two hydrogens sticking out at a certain angle, what is it, 108 degrees or something, I forget, for the water molecule, that the two hydrogens are connected at. And you just make it in terms of balls and sticks. In reality, it's a much more complicated story. And were you to be able to sort of look at a water molecule, you can't do it with visible light, but were you to be able to kind of observe a water molecule, which you can with other frequencies of electromagnetic radiation in principle, at least, you would see the thing wobbling around all the time. It wouldn't be in a fixed position. The oxygen, the hydrogens wouldn't be in a fixed position. It would be wobbling around, and there'd be, in fact, it wouldn't even just be wobbling around. There would be a kind of just different probabilities for the thing to have a slightly different shape. So that's so this whole question about, given some atoms, kind of what shape of molecule do you get, is a really complicated question. For some of the comparatively light elements, it's a reasonable approximation to say that a given element has a certain valence, a certain number of essentially sort of available bonds that it can connect to other kinds of atoms with. That's a reasonable approximation, and that's sort of the first approximation. But the true story is much more complicated. And I gather, I didn't actually know this until very recently, that for the heavier elements, even this picture of having a fixed number of bonds doesn't really work. It's a more complicated story of this whole cloud of electrons rather than a definite direction where it can connect to another atom. There's a sort of complicated cloud of electrons and certain probabilities of having atoms in different orientations relative to the original atom and so on. So complicated story. But when you kind of think about chemistry in terms of this kind of ball and stick type model, you've just got atoms and bonds, you can kind of represent molecules just in terms of graphs or networks. So for example, I don't know, you could represent, and now I'm going to embarrass myself with my poor chemistry, but sort of a simple class of molecules are the alkane molecules, which consist of a sequence of carbon atoms in a chain, and then actually not necessarily a chain, a sequence of carbon atoms with hydrogens kind of hanging off them. And so you get things like methane, propane, butane, going up to hexane, decane, things like that. So decane is 10 carbon atoms in a chain with hydrogens hanging off it. And you can represent that just by this graph that just shows a line of 10 carbon atoms, and sometimes you don't even draw the hydrogens, or you can have these little sort of sprouts coming off to represent the hydrogens. Or you can have something like benzene, which is a hexagonal ring of carbon atoms, and you can represent that by this graph that is just the ring. And for all these different kinds of molecules that are connected together in this sort of standard way with bonds and so on, you can represent them by graphs like that. Sometimes people say, well, there's an extra piece, the so-called stereochemistry, that is how the atoms are really actually arranged in three-dimensional space, and that can get kind of complicated. But in a first approximation, you're just looking at what is the connection by bonds between these atoms. Okay, so that's kind of the basic structure of molecules. Now you might ask, how do you work out in more detail what molecules are like? Well, first thing to understand is molecules are not rigid. Molecules kind of flop around all over the place. And if you, for example, if two molecules collide with each other, even if they might just collide and bounce off, but they're still flopping around because of that collision. And it takes them a while to kind of calm down and stop flopping around. And how do they calm down? Well, that's again a complicated process, because in these molecules, so the sort of the way to say it, sort of the official way to say it, is they're governed by quantum mechanics, and that means that sort of many aspects of how they behave are, for example, quantized. What that means is you might say, well, this molecule, it can be deformed in any way I want. I can just twist it by some number of degrees, and it'll just be that'll be a possible configuration of the molecule. But that's not, quantum mechanics says that you can't do that. Quantum mechanics says at least if you want the molecule to be sort of stable for a long, to be that way for a long time, that it has to be in one of a quantized collection, one of a discrete set of possible states. And so when I say something like, well, the molecule's flopping around and then it will gradually go down to a state with maybe lower energy where it's not flopping around as much, that transition has to happen by a definite quantum event, like the emission of a photon, the emission of a quantum of light, or a quantum of infrared light, or something like that, to make that transition. But the other issue is, okay, so you've got this collection of atoms, and you ask the question, well, how would they connect to each other? How would they, how would that water molecule, you've got an oxygen and a couple of hydrogens, and you put them together, and how will they form into a water molecule? Well, that's a pretty hard thing to calculate. There are mathematical equations that sort of give you information about that, but those equations get really hard to solve. And by the time you've got more than like 100 atoms, to solve those equations from scratch and just say, I throw all these atoms in, what configuration will they end up in, is completely undoable at the present time. You have to sort of approximate that by saying, well, we know roughly how these atoms are arranged. Maybe we can tweak it a little bit using these fancy equations, but we have to know sort of roughly how the things are arranged with the sort of what the rough arrangement of atoms is. And another thing that's really complicated is this. You might say, let's see how to think about this. All right, so in ordinary classical mechanics that we're used to in the everyday world, we always imagine that sort of definite things happen. Let's say you have a thing you've suspended on a spring, the thing's sort of bouncing up and down according to, in gravity, it's going up and down, and the ball at the end of the spring is in a definite place. It goes up, it goes down, it goes up, it goes down, you know where it is. Okay, that's our common experience of the world. But when you go to very, very small objects, what sort of takes over is this idea of quantum mechanics. And in quantum mechanics, you don't have this picture that sort of definite things happen. Instead, there's the picture that there are many, many possible things that can happen. In fact, in some sense, every possible thing can happen. But in the end, you can work out, and so sort of inside the quantum mechanics, all those different things are happening. In our models of physics, we can see this very explicitly. You basically see all these possible paths of history for the universe. All those paths are getting followed. And then the real question is, well, in some sense, intrinsically, all those paths are being followed. And sometimes there'll be a path where two different things can happen. Sometimes those two different things can merge because they both end up in the same configuration later on, etc. So there's all these branching and merging paths that are all possible histories for the universe. And so the obvious question to ask is, well, if that's what's going on, how come we think that definite things are happening? Well, that's a really tricky thing, because part of that story is that we are part of that universe that is branching and merging and so on. So our brains are also branching and merging. So quantum mechanics becomes the story of how does a sort of branching brain perceive a branching universe. That's a complicated thing, and I'm still trying to wrap my brain fully around that idea, slowly trying to get analogies of that and so on, and really try to internalize what it means to have this kind of notion of sort of the branching brain that perceives a definite thing to have happened. And I've sort of, one of the things that we humans do is we generally think that we have a definite thread of experience. We think that a definite sequence of things happen in our life and in the world and so on. And what quantum mechanics is sort of saying is that, well, that's just how we are putting together all these branchings. And maybe there's even senses in which, one's brain, when one sort of doesn't know what's going on, one's surprised about something, and one's just imagining all these different things that could be going on, that's kind of a little bit of a hint about what it's like to not have, knitted together a thread of experience. It's like something weird happened, and I haven't yet put together what it was that happened. And that's a little bit like maybe what's going on when we have quantum mechanics and when we turn all of that, sort of all those threads of history into the definite one thread of experience that we think we have. Okay, what does this have to do with molecules? Well, in this idea that sort of everything happens, and then eventually you find out what happened by perceiving it in some way, how does that relate to molecules? Well, if in these molecules sort of everything is happening, then what sense does it make to have the definite picture of the ball and stick and the water molecule that has this particular shape and so on? How can that make any sense? Okay, this is not an easy question to answer. And this relates to the question of what we really think of about how quantum mechanics works. In the most basic mathematical models of quantum mechanics, which quantum mechanics was invented originally in the 1920s, by the 1930s, there were kind of very precise mathematical characterizations of quantum mechanics, which mostly say there's all this quantum stuff that happens and all these many, many possibilities that go on. And then there's this phenomenon of measurement. And that takes all those many possibilities for what's going on. And then kind of the sort of the hammer comes down and something, and we decide that something definite happened. And which way things come out, there may be a certain probability. We may not know which of those things will come out when a particular, when the hammer comes down a particular time. We may not know. We only may be able to say there's a 1/3 chance that it does this, a 2/3 chance it does that. But there's a definite hammer comes down. You go from all this quantum stuff going on inside to the definite measurement result. That's the traditional view of quantum mechanics. That's the kind of mathematical structure that's been built up to think about quantum mechanics. Okay, well, let's talk about a molecule. It's a bit of a trickier situation because that molecule, it's not as if you let the molecule, in some sense, what seems to be happening is that there is continual measurement of the molecule, that somehow the environment, the chemical environment that the molecule finds itself in, is somehow doing the equivalent of continually making measurements, continually making the hammer come down just a bit. And that's why even though at the quantum mechanical level, sort of all things are happening, all simultaneously together, all these different threads of history, that somehow in chemistry, for reasons not well understood, the sort of chemical environment is playing the role of a sort of very microscopic version of something like the sort of the measuring process, the human observer who is deciding that definite things happened and so on. Somehow chemistry is doing that at a sort of at a continual microscopic level. And that's kind of why we can say that a molecule has a definite form, even though it's operating according to quantum mechanics. Again, this isn't completely understood, and I think there's probably some rather interesting science as one sort of unravels this, particularly with our new interpretations of quantum mechanics and so on. But okay, so this bit of a mystery that it's possible to have a definite form of a molecule, even though there's quantum mechanics going on. But then we can start asking, okay, if we buy into, well, the molecule has a definite form, is there sort of extra wigglings around that come about because of quantum mechanics? The answer is yes, and we can calculate some of that. It's pretty difficult to calculate. We can calculate some of that. Even for the case of water, water is an unbelievably complicated thing. And, in liquid water, for example, you might say, well, water is H2O. Okay, we know that. That means every molecule of water is just an oxygen and 2 hydrogens. You say in a liquid, all these water molecules are just sort of bouncing around. They keep on colliding with each other. They keep on bouncing off, and they're just sort of randomly arranged. Well, it's not true. In water, there's clearly, in liquid water, there's all kinds of structure. There's all kinds of clusters of water molecules that are all sort of connected. I think there are these things that get called proton highways, where you can have kind of a bunch of water molecules all kind of lined up, and you can start sort of transporting electrons from molecule to molecule, things like this. Water is an extremely complicated substance, and it has so when you look at it microscopically in a liquid form, for example, it's got all these different sort of patterns of molecules that are forming just for a moment, just for times like on the order of femtoseconds, a thousand trillionth of a second. They're forming, they're breaking apart, they're forming again, they're breaking apart. That's kind of the structure in liquid water. And it has all kinds of features about that. Knowing why the boiling point of water is what it is, you can kind of calculate the forces between water molecules. You get a completely different answer from the actual boiling point of water, the actual extent to which water can start sort of throwing off, go from the liquid state to break the molecules apart to make steam, happens at, I think, a much lower temperature than you would expect from just calculating the forces between the molecules and so on. So that's a case where we still don't really know why water has all the characteristics it has, particularly in its liquid phase. Now, to talk a little bit more about chemistry, the main thing that kind of happens in chemistry beyond the level of individual molecules is reactions between molecules. Well, what's going on the place where the most reactions happens in liquids. In solids, you have molecules or atoms arranged in this regular kind of typically crystalline type way, so they're all in their place and they're not sort of able to collide with each other and make changes. They're pretty much all in their place. Not always, but that's the most common case. In a gas, yes, there are molecules always bouncing around, but the density of molecules is comparatively low, and so it isn't as if those molecules, let's say the molecules they're always colliding with each other. They go only a tiny distance in typical pressure of gas, like in the air, in the atmosphere. They're going only a very tiny distance. Molecules go only a tiny distance before they collide with other molecules. But most of the time, those collisions are elastic in the sense that molecule collides with another molecule. The molecules stay together. They don't fall apart. They don't start exchanging atoms or electrons or anything like that. They just bounce off each other. So if you are going to have a chemical reaction happens when the two molecules collide, but instead of just bouncing off each other, they do some complicated thing. They change their shape, they exchange atoms, their bonds get smooshed and break apart, and they get reconnected somewhere else, and so on. And just in order to have that happen, there are just vastly more collisions that happen in liquid. So that's the place where it's more common to have chemical reactions. And then the whole question of sort of how those chemical reactions work, and when the molecules hit at particular angles, they need to be hitting at the right angle for the reaction to happen, and so on. One of the things, and I think maybe I've talked about this before, but I'm steadily learning more about this. One of the biggest uses when you're going to have a reaction between two molecules is, do they hit at the right angle? Do they hit so that the particular piece of that molecule sticks into this hole in the other molecule and the atoms can exchange their bonds and things like this, or not? And so one way to have that happen is to have a catalyst that is something like a metal that's a surface, and one molecule will kind of get embedded in the surface and kind of expose itself in a particular direction, and then another molecule will come and be able to stick itself in that direction. And so one molecule is fixed, and that means only the other molecule has to be in the right configuration, whereas otherwise, rather than both of them having to be happen to be in the right orientation. And when it comes to biology, one of the things biology has become very expert at is arranging molecules to be in the right orientation and the right place to actually have reactions. And so enzymes, the catalysts that get used in life, mostly proteins, are arranged to have all these kind of holes and crevices and places where one molecule will attach itself in this way and expose itself in just the right way that another molecule can come in and have a chemical reaction with it. And life even does much more elaborate things. It even has all of these tubes that are in the sort of the cytoskeleton, the sort of internal fibrous skeleton of biological cells that are actually moving molecules around. They're just moving them down like a train track, so that the molecules end up in the right place at the right time to have a chemical reaction. So that's a little bit on. So in some sense, when we talk about, for example, a liquid phase reaction, we're talking about molecules in a liquid, they're bouncing around, they're reacting with each other. in biology, it's almost like a biology phase reaction, because it's almost like there are all these enzymes and microtubules and all this kind of thing, which are kind of more machine-like ways moving molecules around so that they can undergo reactions. And there was an enthusiasm in the 1980s, I guess, particularly for early kind of nanotechnology and molecular manufacturing. And kind of the idea there was, could you take things that we know from sort of traditional mechanical devices, and could you shrink them down and implement them with individual molecules and sort of make what one might think of as sort of a machine phase, where instead of it being liquids where the molecules are sort of bouncing around randomly, or solids where all the molecules are arranged, in a very regular way, something where there's sort of an intentional machine-like arrangement of the molecules, where there's, cogs and levers and things like that. And you might say, what a bizarre idea to make, make gearing, for example, out of molecules. But actually, that's something that happens in the little tails, the flagella of bacteria and things. You'll find these sort of motors that are made with kind of a fixed gearing. I think maybe they have 13 sort of teeth on the cog type thing in certain cases. And so that idea of sort of making mechanical stuff out of making our traditional mechanical stuff like gears and so on out of molecules, it's something one can imagine doing. Whether that's the best way to make use of molecules to achieve things we want to achieve, that's a different question. In traditional chemistry, that's not what one's usually doing. One's just saying, throw these molecules together, they will react. You can think about it as this graph plus this graph will be reconfigured into that other graph. If I thought about it that way, sort of 50 years ago when I was learning about chemistry, I probably would have been much more enthusiastic about chemistry. Instead of just you memorize these kinds of this white powder and that white powder gives this other white powder. The more interesting, well, at least to somebody like me, is this idea that you can, just like we can write down like a mathematical expression, x squared plus 1, and that's a definite kind of abstract thing that we can do things to. We can also say, well, we can write down this graph that represents a chemical, and we can do definite things to that graph. So, for example, just like we can transform, we can say we've got x squared plus 1. We can replace x by x plus 2 or something and see what we get. Well, you can do very much the same kind of thing in a molecule. You've got this graph. It's got some piece of the graph there that might be just a single atom, or it might be a collection of atoms. You can say, let's replace that piece of the graph by something else, by another piece of graph. And that's essentially what happens in chemical reactions, is there's a replacement of one piece of graph by other pieces of graph, and so on. And that's a very sort of formal way to think about it. It's not precisely correct. Actual molecules are sort of floppier and more complicated than that. But it's a good first approximation. And there's lots of kind of reasoning that you can do at that abstract level. And that's kind of a lot of what people learn in learning things like organic chemistry and so on. So, I think that's but the thing that, in a traditional sort of chemistry setting, it's like molecules are just rolling around randomly and they might happen to connect with each other. When we start thinking about kind of machine-like situations, which is what biology has managed to set up in many cases, it's much more like this molecule is going to be made in this place. It's going to be moved along this kind of conveyor belt by other molecules. It's going to be set up to do this. It's going to be connected into this other molecule. This will happen, et cetera, et cetera, et cetera. Now, an interesting question is that sort of story of there's a machine and it operates this way. The fact that we can tell such a story it's not obvious that that's the only thing that's going on in the chemical system. It could be that there is some such story to be told, and maybe biology has tried to arrange it so that that's an important story, but there's probably more to it. There's probably more that's at the level of the kinds of things that quantum mechanics talks about, even though it might not operate according to quantum mechanics itself, where there are many possible paths for how this molecule can be oriented and can react with other ones and so on. And that becomes a much more difficult thing to analyze, and it's something for which we don't have very good sort of human narrative description capabilities. But it's something where I suspect that that's going to be important in understanding how one can, for example, do computations efficiently with molecules and such like. let's see. Okay, there's a question here about commenting on chemistry. Parmenides is commenting about how great chemistry is and how important it is to the world. For sure, it's you know, molecules are our raw material, and chemistry is our way of manipulating molecules. Maybe eventually we will have a much more sophisticated way of manipulating molecules. Right now, it's just you throw these buckets of molecules together and you hope they react, rather than this much more structured, programmable way of having molecules interact, where you really sort of know what orientation the molecule is in and you know what it's going to do, and so on. You know, eventually one might have a situation where one can really have what one might think of as programmable matter, where you say, here's this thing, and I can really specify, just like on a computer, I can tell it do a different computation, I can just feed it in a program to say, fixed hardware, just do a different computation. One might imagine that that same kind of thing would one day happen for molecules and matter, that one would be able to say, okay, you've got a collection of molecules here, you've got this whole, you've got molecules, et cetera, et cetera, et cetera. I feed in a program, you know, I flash light at the thing or something in some complicated pattern of flashes, and the thing says, okay, I understand that program. Now I'm going to configure myself in this or that way at the level of molecules. In other words, that you might be able to program the actual operation and structure of matter. Something I've been curious about for a long time. Could you make a machine that would just make any molecule? You give it a drawing of the molecule and you say, go and make this molecule. Usually when people think about synthetic chemistry, their way of making a molecule is some very elaborate thing where, oh, you have to, you know, if you throw in this kind of molecule, then it will lop off this arm that's on that other molecule. Oh, but you don't want it to cut out this little piece in the middle, so you have to put in a protecting group on the molecule to stop it having, to stop the other molecule that you throw in being able to get at that part of the molecule you don't want to get at. Then you do this, then you send in some other molecule to get rid of the protecting group. And it's kind of a whole sort of puzzle story. Whereas one could think that one day it would be really a question of just, you have this molecule, you have this soup, and you're basically, I don't know how you communicate with that soup. You know, in the case of a computer, we kind of, you know, we're just using electrical signals that are very sort of precisely arranged to do what they do. I don't know how you communicate with your kind of super molecules, particularly. Well, it probably wouldn't actually be in a liquid phase. It'd probably be in some kind of weird machine phase where the molecules are dynamic. And in fact, my guess is what it would be is in a standard solid, the molecules are just lined up, like in a crystal, they're just all lined up in a particular configuration. In a glass, for example, also pretty much a solid, the molecules are there, but they're all sort of stuffed in randomly, just like some, you know, ball pit or something where you've thrown a bunch of balls in randomly, but they're still all jammed together. Well, one can imagine a phase of matter in which, I should say in a liquid, obviously, the molecules are kind of running around. They don't get very far. They collide with other molecules, but they're basically, they're basically randomly running around. So you could imagine a phase of matter in which the molecules aren't fixed in place, but they have complicated little, you know, dances that they do, where, you know, the thing is reconfiguring itself locally, and it just, the molecules are moving around, but it is still a quite orderly thing. And the molecules, let's say in their steady state, the molecules are all doing some kind of weird little figure eight dances with each other, with neighboring molecules, and that's happening throughout the material. And then you kind of flash light at it, and suddenly they change their figure eight configurations, and they start going to neighboring molecules, and they start implementing a different kind of rule for operation. One could imagine, I remember thinking about this actually, 40 years ago now, of whether one could make one of these cellular automata that I've studied a lot, where you just have a collection of cells, and each cell is updated according to a fixed rule, depending on the values of its neighbors. Could you make that out of individual molecules? And could you, for example, have something where there is dynamical, it's a it's a continuously kind of molecular scale moving thing. And you flash light at it or use some electrical signal of some kind, and it changes. It's the rule that it's using to determine how those molecules sort of move around. That would be kind of a version of programmable matter, and it will be a very weird thing. We don't know how to make that kind of thing yet. Potentially with programmable matter like that, you could have it, reconfigure itself in all kinds of ways. Maybe it starts at the level of molecules, but then it builds itself up to something which is a large scale kind of walking creature or something. I know there are science fiction movies that have kind of effects that look a bit like that. And one can imagine that that might actually be possible in practice, to have something where one can sort of determine how the things work down to the level of molecules. But that's not our current state of the art in chemistry. Our current state of the art is to make things. You have to really do this kind of very indirect thing of throwing things in and hoping that they interact in the right ways. I think this issue about sort of what might be possible if we could do things at a molecular scale. I mean, right now with computers, we know the amazing power of being able to program things, being able to have one fixed piece of computer hardware that you can program to do all these different kinds of things. If we could do that with matter down at the level of individual molecules, we will be able to do spectacularly more things. And I think that the question of the only case that we have right now where things are sort of happening at the level of molecules and sort of where there's essentially computation at the level of molecules is what's happening in biology. But if we could generalize biology to arbitrary things with programmable matter, spectacular kinds of technology would be possible. It would sort of, potentially it will put biology to shame, so to speak, in the sense that biology has proudly progressed for a few billion years, sort of slowly through biological evolution, tweaking to get a little bit better at doing this or that thing. If we start thinking about kind of the picture of, well, if we could just program anything at the molecular scale, what could we program to have happen? That's an interesting question, and I don't know. It will be interesting to think through what would be some of the first technological wow moments for being able to do that kind of thing. I think some of the ones that we would care the most about are ones that interface with us humans and interface with the biology that we have and the molecular biology that we have, and sort of are saying, well, don't use, you've got organs that do molecular scale filtering of things in your body or whatever else. That's a goofy way to do it. Here, there's a better way to do it that you can make with sort of programmable matter, and that you can interface to the existing biological structures that you have. So I noticed that Parmenides was commenting on the effect of chemistry on the history of humanity. And obviously it's very great. I think, what are the estimates? If it was, if we didn't have, agriculture and all those kinds of things, if we hadn't figured out how to optimize those things, the Earth might support 10 million people, and that's about it. We're at nearly 8 billion and counting, so to speak. And that's kind of a big effect of, well, both theories of, principles of agriculture and chemistry and things like fertilizer and so on. And I think that it is an interesting question, just being able to feed people is one big effect of chemistry. Other things that have happened in chemistry that are really important, I suppose, are, well, lots of industrial processes for making things. You have, whether it's going from sort of the ore of rocks that have a few atoms here and there of iron or aluminum or something like that, to actually, here's a big block of aluminum. That's another kind of chemistry-like process, to kinds of things where we're doing, well, making, for example, one thing that was sort of important 100 years ago or so now was plastic. The fact that one could just make a completely new kind of material that was useful for different purposes. It wasn't made of wood. It wasn't made of, it wasn't made of metal. It was something where one had for the first time arranged these long molecules, that's what plastic is made of, created these long molecules and made them into a material that one could sort of create from scratch. That was sort of the remarkable thing that was plastic. And there are obviously other kinds of there are other kinds of sort of new materials. There are ones to do with carbon nanotubes and things like that, which are possible, might be significant now. But I think one of the things that sort of the ultimate thing is the programmable version of matter, where, well, instead of it being just this fixed arrangement of a molecule, it's something where it has a continual sort of choreography inside, and is where that's specifiable in some external kind of way. And that becomes sort of a quite new level of sort of generalized chemistry, sort of a combination of computation and chemistry that I think has some sort of interesting, as I say, to imagine what becomes possible in that situation. I think, as I say, the sort of the interface with biology will be pretty important. I also suspect that, people have talked for a long time about, can you grow a house? Could you imagine, I mean, people have these sort of ideas of, if we could manipulate biology more, we could, instead of having a house where you have to actually construct it and you've got, pieces of wood that you make from dead trees and things like this, imagine that you could have something where you've got sort of a biological organism that is arranged to grow in the shape of a house. Could you do that? And you could imagine, if you have programmable matter, that instead of sort of piggybacking on the back of, sort of the biologically grown house where you have the problem of, I didn't feed my house enough today. It's in a bad mood type thing. I think one would have all kinds of, whatever. It's piggybacking on top of biology, that one could imagine something with a sort of truly programmable matter where you could say, okay, I mean, another thing that is the case is that right now, this is probably the most significant thing, that right now you make something, you manufacture it, it's a certain shape. Maybe you have a dye that you use to, you pour plastic into a dye, you mold it in a certain shape. Maybe it's liquid when it starts out, it cools down, then it's this plastic thing that's this shape. Or something where you're connecting together these rods and you're welding them together or whatever else, it's a definite shape. The things we have right now, most sort of manufactured things they're kind of definite shapes. Maybe they have levers and gears and so on that can move, but they're basically a definite shape. But imagine in a world where you're dealing with programmable matter, you get this blob, and the blob, you just, you take it home and it's just, you probably wouldn't have to do that even. Everybody would have lots of these blobs of programmable matter. You take the blob of programmable matter out, you flash its program at it, and pretty soon it reconfigures itself, and then it's a, it's a paperweight, or it's a thing, a hairbrush, or it's whatever else it is, and that all happens as it's managed to configure itself by just moving its molecules around under program control, so to speak. And I think that's it's sort of the kind of thing one can imagine in this sort of chemistry meets computing future in that case. I think the thing that then becomes an issue is, okay, you're making this thing, but maybe this thing needs iron atoms in it. Maybe it's a thing that needs some properties that require particular kind of atom. So then you'd have to have the supply of different kinds of atoms. And it's an interesting question, to what extent most of the things that we care about happening with objects are actually more about the shapes of those objects and their mechanical properties, or maybe their electrical properties, than they are about, really, are they made of aluminum or iron or whatever else? And is it possible that with sort of programmable matter, that it's just carbon and hydrogen and oxygen, let's say, and that's it, and that you can kind of get everything you want just made in terms of those elements? That's sort of part of the story of plastic, is that you really are using mostly those elements to make things, and you can sort of configure them in lots of different ways. And so that would be a question, is whether in the case of, I don't know, transporting oxygen in our blood, we use hemoglobin, which is mostly the sort of cage that's a protein, but inside that cage is this little hole in which there's an iron atom. And that iron atom is important for the way that our hemoglobin works to transport oxygen around our blood. But I don't know if that's actually necessary, or whether there's some way of having the same effect with exactly the right configuration of carbon and oxygen atoms, making the right kind of cage, the right kind of sort of tube that lets oxygens through and so on. So I don't know to what extent it is necessary. I mean, we have available to us elements other than, let's say, carbon, hydrogen, oxygen, but I don't know to what extent that's truly necessary to achieve the things that we want to achieve. It's sort of an interesting question. If you have a computer that we kind of now know that you can make a universal computer out of very simple components. You don't need all of the complicated circuitry. You can make it out of just some simple set of rules. In chemistry, one might have imagined, well, you at least need all the kinds of atoms, the whole periodic table, but maybe that isn't true. Maybe if what you're trying to do is for many purposes that we might define as the purposes for which we want to use matter, we actually don't need all those other kinds of atoms. We can achieve those things by the appropriate configuration, by the appropriate programming of just, let's say, carbon, hydrogen, and oxygen. Robin is saying, isn't organic chemistry the study of programmable matter? Well, the distinction that I'm making is that in chemistry, you're not able to, at the level of an individual molecule, just tell it, go do this. You're having to do that very indirectly by smashing molecules into each other and so on. Let's see, maybe one more. Oh, gee, we've got a bit more time here. Let's see. Aaron is asking, can you tell the story of traveling through a central processing unit on a computer from the electron's perspective? Interesting. Well, interesting. So the first thing to explain is electricity is a flow of electrons. But so in a metal, for example, there is a metal has a bunch of atoms of that metal, let's say copper, something like that. And those atoms are arranged in an array in a crystal. And those atoms have certain electrons which are very tightly bound to the nuclei of the atoms, and they're not going anywhere. But what happens in a metal is that some of the outer electrons that are further away from the nucleus, they end up being sort of, there's an overlap between neighboring atoms, and eventually you form what's called the conduction band, where essentially the electrons that are sort of that far away from their nucleus aren't bound closely enough to any one nucleus. And so they're able to float freely through the metal. And so that's kind of what leads to the fact that a metal can conduct electricity, is that the electrons are not attached. Some of the electrons are not so tightly attached to their individual atom. They're able to just float from atom to atom in this conduction band. That's kind of how things work in a typical metal. And the electrons, as they flow through the crystal, they're usually, the reason they don't flow completely freely is that they keep on, as an electron is kind of moving through the crystal, it keeps on running into things. It keeps on bumping into, oh, there's an atom in the way. Oh, there's this kind of imperfection in the crystal. There's these different things. It keeps on being scattered. So the electron, let's say when you put a voltage on a wire, what the voltage is doing is it's making an electric field that will pull electrons through the wire. But the electrons don't just whiz through the wire at sort of maximum speed. They keep on getting scattered by things. The electron is being pulled by the electric field, but it keeps on hitting something and then it scatters away. And that process of scattering is what leads to resistivity of materials. that's the thing that makes it be the case that when you put a certain voltage on the wire, the current, the flow of electrons through the wire is there's only a limited flow of electrons through the wire. So there's this formula, V equals IR, Ohm's law, or put it a different way, I, the current, the rate of flow of electrons is voltage divided by R. And so that's telling you that as there's more resistance, there's less current. And the resistance is the amount of scattering that happens in these electrons. So what's going on is the electrons, they're being pulled through the wire, but they keep on running into things. And the amount they run into things depends, for example, on the temperature of the wire. So as you decrease the temperature, they will tend to be less sort of random stuff going on in the wire, so the electrons will flow a bit more freely. There's a phenomenon that happens at very low temperatures, a few degrees above absolute zero. At absolute zero, it's sort of in a first approximation, all this running around that molecules do that defines temperature more or less stops at absolute zero. But there are particular materials called superconductors where electrons do flow freely through the material. They don't get scattered by anything. They can just zoom right through. So they have essentially zero resistance. They have sort of infinite, that's not quite it. They have, let's just say they have zero resistance, and electrons can move. You can like have electrons that you put them in a loop in a kind of wire of superconductor, and they just keep going around for months and months. Whereas in an ordinary wire, at ordinary, they would be, the electrons would kind of be stopped by collisions and by resistance, by resistivity. Okay, so that's how an ordinary wire works. A semiconductor, in a metal, there is a conduction band. There are some electrons which are delocalized. They are not localized to individual atoms. In an insulator, something which doesn't conduct electricity, you have a situation where essentially the electrons are closely bound to every atom. So you can't tear an electron. Even if you put a big electric field on the material, you can't, the electrons will just be stuck. They're not moving, they're just stuck to an atom. They don't move. They might move a tiny bit away from their atom, but they don't get to jump to the positions of other atoms. At least not until you put a huge electric field and then you have a breakdown of the material. That's what lightning strikes are and things like that. But normally in an insulator, electrons are just bound to their atoms. Okay, there's an intermediate case, which is semiconductors. And in a semiconductor, the electrons are basically bound to their atoms, but there is a certain what's called band gap. If you put a certain voltage on the material, you'll be able to promote an electron from this from its sort of tightly bound configuration into the conduction band. If you give it enough energy, it'll start sort of flowing freely through the material. In the case of silicon, the band gap is 6 volts. And so if you that's why a lot of electronics runs on 6-volt batteries and things, 9-volt batteries, things like that, is because that's what you need to get the electrons promoted into the conduction band. And so sort of the big idea and I'm eliding a whole bunch of stuff here, but the more or less the big idea of using semiconductors is that you can kind of switch on and switch off conduction by whether you're promoting these electrons or not. The way it really works, there these this idea of doping where you put other materials, into semiconductors, and that changes where the conduction band is. It's a slightly longer story, but in the end, in a CPU, the sort of the key element of these things called field effect transistors, and they're made from semiconductors. And essentially, what happens is they have it's called the source and the drain. You have a source of electrons, and they're sort of going towards the drain. And there's a thing, the gate, which is another sort of wire that goes across. So there's sort of like a wire going one direction in this field effect transistor. And then there's another wire that goes 90 degrees across it. And that other wire, when you put a voltage on that gate, you can determine whether a current will flow from the source to the drain. And that switchability, that's the key piece of functionality needed to make an electronic circuit And when you put 1 billion of those together, you get a modern microprocessor. And the design of exactly how those field effect transistors, those switches are put together, that's the thing that you have to kind of, you can start talking about logic operations. The most basic operation that is done by one of those field effect transistors is either a NAND or a NOR operation, basically saying if you've got 2 inputs and if it is not the case that both of the inputs are have a voltage effectively, then have an output voltage, but otherwise don't. And that operation, if you put together NAND gates, you can make all the standard logic operations and you can create the things that you need to make a microprocessor. Okay, so at the most basic level of electrons, things are happening where the electrons are being promoted into the conduction band and then they're dropping down from that and they're being stuck somewhere. And it's kind of, I think from an electron's point of view, it's kind of a lot of stop-start type stuff of, oh, this circuit, this wire started having a voltage on it. Okay, now we can go. I'll move on to the next place. I'll move on to the next gate. And then I'll go, by the way, the whole sort of assembly that makes an AND or an OR or an AND or something is usually called a gate. I guess I've never even noticed the confusion of the fact that a single component of a field effect transistor is also called a gate, but they're a little bit different. They're ultimately contributing to the same thing, but a little bit different in detail. But in any case, so from an electron's point of view, I think you're kind of moving through wires, but you keep on stopping, restarting, etc. Now, it's a little bit of a philosophical issue. Are you the same electron when after you got stopped and you get stuck to an atom for a while, and then you start moving again? Are you the same electron or not? And that's certainly a sort of philosophical question of which, at the level of a human, there's enough pieces of us that the fact that we might be being recreated as we move through space is we still think of ourselves as definitely us. But if it's a single electron that's getting stopped and then restarted again, it's a little bit less clear because all electrons seem to be identical. It's a little bit less clear whether we would say it's the same electron. But let's just, for poetic purposes, let's say it's the same electron that's getting stopped at some gate. It's going to start again. It's going to move as voltages change. Things happen. So what is going to happen on a typical electron? So the power supply of your computer is like generating voltage. It's pushing out electrons in this current, and those electrons are going in, and some of those electrons will be used to, some of that current is going to go to the CPU, the central processing unit, and let's pick a thing that an electron might be doing. Well, gosh, as it comes in, actually, it's kind of an interesting way to think about it. I mean, what will happen is, as the electrons come in, they'll be sort of shunted to different places to do different kinds of things. And I think that shunting is basically going to happen at random, depending on, so for example, let's say we got a wire coming in and it splits in 2. Which way is the electron going to go? Is it going to go left or right? I think that's going to be pretty much just randomly determined. That is, the electron, there's nothing about that particular electron that's going to say, I'm one that's going to go down the left branch. I'm going to go down, one's going to go down the right branch. But what's going to happen is, it's kind of like maybe water flowing through a stream, and the stream breaks in 2, and it's like, which way does the water go? Well, some of it goes one way, some of it goes the other way. Maybe it depends in detail whether that molecule was over towards the left-hand side of the river or towards the right-hand side of the river, and so on. So I suspect that's the same kind of thing with electrons. And then as the electrons go into the circuit, well, gosh, what will happen? Let's see. I mean, usually when you design a circuit, you imagine that there's kind of a rail which has a certain voltage, which has electrons that, and then you're kind of getting this whole thing where you have two sort of a 0 volts and a plus whatever it is, 6 volts or something, and you've got sort of all the electrons are being dragged through from one to the other but that dragging through is through this whole elaborate structure that is the circuit that you're dealing with. So I kind of think it will be kind of like you're kind of moving through this whole collection of different pieces of the circuit. Now, if you ask, well, what happens? Yeah, I think the most significant thing is the clock frequency of the computer. So what's going to happen is every the kind of, okay, electrons, go move to your next spots. That's going to happen every time the central clock of the computer has one sort of tick. And so a typical computer, I don't know what the computer that I'm using right now, I would guess it's a 2 gigahertz-ish clock. That means 2 billion times a second, the electrons get to move to the next station, so to speak. And so what's happening is, like, they might be fixed, okay, you're in this configuration, okay, now you move to the next one. It's going to take you a small amount of time to move. The electrons don't move instantaneously. They move at a small fraction of the speed of light through the wires. I think maybe typically, maybe a tenth the speed of light, if I remember correctly. I mean, it depends on lots of different things. But so when the clock says move, the electrons are going to move just a tiny bit. They're going to get stopped by some gate somewhere, and they're going to move to the next position. And then they're going to be there. Then they'll wait there. Then the clock ticks again. Then they'll move to the next position, and so on. And I think that's that would be kind of the picture of what's going on now. And the whole logic of what's happening in the circuit would be sort of seen by the electron as, oh, there's no voltage that's pulling me to the next place. I'm just going to sit where I am for the time being, I think. So that would be my basic picture of yes, M9 is pointing out field effect transistors use voltage at the gate to make a field that pinches off the flow of current from the drain to the source. Is it from the drain to the source or the source to the drain? I think that's what we get for having electrons have negative charge. That's absolutely right. And if I think hard about this, I could probably tell you in terms of how that works in terms of the doping of semiconductors and so on. But that's exactly the right picture. Is you're kind of stopping what's happening is, okay, let's see, what's happening is, I have to think about this more carefully, that there are, you can adjust this band gap a bit by having impurities in the silicon crystal, for example, and you can have p-type or n-type impurities, which are basically, so silicon has valence 4. So silicon has sort of four electrons that are kind of available from each silicon atom. You can put in impurities that have either 3 or 5 electrons available, and those lead to a change in the amount of energy that you need to give to an electron to reach this conduction band. And that's and when you actually make a circuit, what you're doing is you're putting it's more complicated than this. I have to think this through. It's one of these things where when I probably haven't thought about this in a couple of decades, so I can't do it well instantly. It's okay, and it's probably the best I can do for right now. It looks like it's time for my next thing here, but I see a lot of interesting questions, which we can save up for next time. And I'm just thinking whether I can say anything. I like this question of the electron's view of computation, so to speak. I think the the case of some kinds of things, like in a memory chip, I think one will have a situation where sort of electrons are running around, kind of storing that one bit for one, and then every so often something will come in and read that bit, and maybe that electron will be like, I've been storing that one bit for the last 2 days, and finally something will come and take that electron away and say, okay, you're going to deliver your oneness, so to speak, to some other part of the circuit, and another electron will come in and take your place storing that one bit, and so on. I think that's kind of might be the electron's eye view of what's going on. I have to say, I was curious recently. I need to get back to this. I was in trying to understand sort of questions about consciousness. I was trying to kind of think about what is the experience that a computer has. I hadn't gotten down to the level of what experience an electron has. That's an interesting further level. I was just thinking about the experience that a computer has of interacting with time and the outside world and so on. Anyway, a thing to talk about another time. Maybe I'll talk about that another time here. It would help me kind of collect my thoughts about how a computer consciousness kind of feels about the world. All right. Well, thanks very much. Lots of interesting questions. I enjoyed trying to think some of these things through. This is I have to say, it's an interesting for me. These live streams are an interesting kind of experience because, I'm trying to answer these questions sort of in real time without any outside, information, and these are and trying to sort of piece together some of these more complicated things. It's often the worst when it's something which I think I've understood for decades, but I don't think I've ever explained it to anybody. And it helps me a lot to actually have this opportunity to explain it, even though it's a little bit, I make it a bit more difficult for myself by insisting on just trying to say it directly, rather than, thinking for a long time about kind of how to arrange the pieces. But so I hope what I'm communicating is useful. It's, as I say, it's helpful to me in being able to collect my thoughts. I think, for example, today I talked about a number of things to do with programmable matter that I don't think I've ever really put together in quite those ways before. So thanks for inducing me to do that. And see you again another time.